Hello, I'm Deb Cronin, and this is a presentation of my work, A Post-Saccade Blank Interferes with Transsaccadic Displacement Detection in Real-World Scenes. Each time we move our eyes, the pattern of information falling on the retina changes. During each eye movement, our visual system is also suppressing visual input. However, we do not perceive a series of isolated snapshots from each fixation. We perceive a stable, continuous visual world. This perceptual stability persists even when there is instability during the eye movement. For example, we can ask participants to move their eyes to a peripheral square. While their eyes are in motion, we can move that square away from its original position. Remember, the visual system is tuned down during eye movement, so participants don't see this movement. After participants' eye movements, we can ask them things about the square's position. We can ask them which direction the square moved during their eye movement, or did the square move at all? And most of the time, participants will have no idea. They'll guess which direction it moved, or they'll say no, it didn't move at all. The results of experiments using this paradigm are taken as evidence that the visual system assumes that the world is stable during an eye movement. In a series of classic experiments, Deborah and colleagues demonstrated a mechanism by which this assumption can be broken. Using a paradigm similar to the one I just showed you, Deborah introduced a blank period at the conclusion of the eye movement. So participants are moving their eyes to the peripheral saccade target, and the saccade target disappears before the participants' eyes land. So they essentially land on a blank screen. And after a short delay, the saccade target returns, and you can again ask which direction the square moved, or did the square move at all. So we conceptually replicated this classic effect in our lab using the second question, did the square move? And adding that post-saccade blank significantly improves participants' overall displacement detection accuracy. As you can see, in the no blank condition, participants are performing worse than in the blank condition. And because we used a detection task, we were also able to use signal detection theory to determine participant sensitivity to the displacement. Unlike accuracy, sensitivity takes into account participants' guess rate. So in this graph, sensitivity, or d prime, is plotted on the y-axis, and the displacement distance, or how far the square moved in degrees, is plotted on the x-axis. As you can see, participants were significantly more sensitive to displacements of the saccade target object with a post-saccade blank compared to without a post-saccade blank, and this difference is very clear at this 1 degree displacement. We can also look at participants' criterion or response bias. The way that we calculated criterion, positive values mean that participants were biased to respond yes, the square moved, and negative values mean that participants were biased to respond no, it did not move. So without a post-saccade blank, participants were significantly biased to respond that the target did not move relative to the blank condition. Now, aside from a few notable exceptions, most of the research in this field has been done using simple stimuli, one or a few shapes on a plain background, much like the experiment I just showed you. We wanted to see whether this blank effect would hold up in more complex stimuli, real-world scenes. In our first experiment, participants began each trial fixating a cross at the center of the screen. A scene appeared, then the cross changed color to indicate which direction they should move their eyes. Red meant right, blue meant left. When the cross disappeared, participants were asked to move their eyes about halfway between the center and edge of the scene in the cued direction. And we had an RA monitoring participants' eye movements to make sure that they were generally following this instruction. While their eyes were in motion, we shifted the scene 2 degrees in the opposite direction of the participant's eye movement. Generally, stimulus displacements in the opposite direction of an eye movement are more noticeable than stimulus movements in the same direction as an eye movement. And importantly, the spatial location of the scene on screen did not change. The scene moved behind the gray surround, kind of like viewing it through a window. So let me back up so you can see the shift if you missed it before. So at the end of their eye movement, participants responded whether they thought the scene had moved or not. We called these no blank trials, and according to previous work, these trials should be difficult. Participants should have a hard time detecting movements of the scene because of the assumption of stability. But we also included trials with a post-saccade blank and a within-subject design. These trials proceeded in the same fashion. Participants began at the center of the screen, and then moved their eyes halfway to the edge when the fixation cross disappeared. However, before the conclusion of their eye movement, the scene disappeared for 250 milliseconds. When the scene reappeared, either in the same position or displaced 2 degrees, participants responded whether they thought the scene had moved or not. Alright, so some predictions. Previous work suggests that the post-saccade blank should help participants' displacement detection performance relative to the no blank condition. And at least in one measure, it does. Accuracy is higher in the blank condition than in the no blank condition, though it is quite low overall. At first we thought, great, we replicated the effect, but it turns out that this accuracy difference is misleading. When we look at sensitivity, participants are actually significantly more sensitive in the no blank condition than in the blank condition. This is the opposite pattern of effect that we saw in our simple stimuli experiment, and it sits in contrast with previous work. The post-saccade blank decreased sensitivity to the scene displacement. When we look at the criterion for these two conditions, we can see that, as was the case in our simple stimuli experiment, we see a difference between the two conditions. Participants are significantly less likely to respond that the scene moved in the no blank condition than in the blank condition. So the blank is again raising the likelihood participants will respond that the scene moved. So a post-saccade blank did not improve sensitivity to scene displacements, and instead it significantly increased the likelihood participants responded that the scene moved even when it did not. So in effect, the post-saccade blank increased both the hit rate and the false alarm rate, decreasing sensitivity. So we were surprised that we weren't able to replicate the classic blanking effect. And so the first thing we thought was maybe the task is just too hard. So we did a second experiment with the same stimuli, the same task, but added a 4-degree displacement condition. So once again, we're plotting sensitivity on the y and displacement distance in degrees on the x. And when we look at sensitivity for this experiment, some interesting things happened. First, in the 4-degree displacement condition, we replicate the effect we found in the scene experiment. Participants have a significantly higher sensitivity in the no blank condition compared to the blank condition. When we look at the 2-degree displacement condition, however, the difference goes away. Participants are equally insensitive to displacements in both the blank and no blank conditions, so that the interaction between blank and displacement distance is significant. Why do we find a similar effect in the 4-degree displacement to the last experiment, but not in the 2-degree displacement condition? Well, when we look at participants' response bias, you can see that participants are more likely to respond that the scene moved in the 4-degree displacement condition than in the 2-degree displacement condition of the no blank condition. This is a significant difference. So what we think is going on is that participants are effectively never responding that the scene moved in the 2-degree no blank condition, and in the 2-degree blank condition, they're guessing that the scene's moving, whether it's moving or not, lowering the sensitivity to the same level as the no blank condition. So they're overlapping in their sensitivity. But meanwhile, in the 4-degree conditions, we see the same pattern of effect that we saw in the first scene experiment. So in making one of our displacements easier to detect, we made the other less detectable, or at least less reportable. In both of our scene experiments, a post-saccade blank did not improve sensitivity to scene displacements relative to the no blank condition. This is in contrast with previous work in simple stimuli. So here's our first experiment where we use simple stimuli, and as you can see, the pattern of effect reverses for our two scene experiments. Instead, the blank changed response bias, making participants more likely to respond that the scene moved regardless of whether it did or not. And interestingly, we found that same pattern of response bias in our simple stimuli experiment. Participants were just more likely to respond that the stimulus had moved with a blank across all 3 of our experiments. And again, as you can see, the data from all 3 experiments shows the exact same pattern of effect. So maybe the complexity of scenes makes it much more difficult to break the assumption of stability, and that just prevents the blank from being effective. Now, there are obviously many differences between simple stimuli and scenes. There are many differences between our paradigm and Deubel's original paradigm. So first, scenes are vastly more complex than simple stimuli. Perhaps the sheer amount of visual information is too much to keep track of across an eye movement. Or maybe the semantic content of the scene interferes with participants' ability to detect displacements due to something like boundary extension. In our paradigm, participants' eye movements were self-directed, while in previous work, participants are directed to a specific saccade target. That was also the case in our first experiment with the simple stimulus. There's evidence that directing participants to an explicit saccade target may change their sensitivity to changes in the scene. Maybe if we had cued participants to move to a particular object in each scene, we would have seen something more like what we see in simple stimuli. Finally, making an entire scene disappear during the blank period is quite different than having a small square go missing. Perhaps there's something about the re-onset of the scene that overwrites whatever sensory representation is being maintained about its previous position. So while we have a lot of work left to do to figure out exactly why this is the case, the bottom line is scenes and simple stimuli are not equivalent, and effects we find in simple stimuli do not always scale up to scenes in a straightforward way. In general, scene stimuli are a closer approximation of our normal visual experience. If the classic blank effect, or any other classic effect, doesn't scale up to scenes, how much does it tell us about what our visual system is doing in a complex visual environment? Thank you very much for your attention, and thanks to my RAs and the NEI for funding this project.